So far this chapter, we have done confidence intervals for the proportion, where you're trying to get the interval of that, what the proportion of maybe male students were. So you'd look at saying that the proportions between these two values. And when we were doing the proportions, we were able to use the z-scores to help us. And when we were doing it on the calculator, we were doing, I don't remember what it was called exactly, the one proportion z interval was what we were looking at. Then we did the confidence interval for the means. We had to pay attention to whether we knew the population standard deviation or whether we didn't know the population standard deviation. And that made that difference of whether we were able to use the z-scores or we had to use the student t-scores. And those student t distributions, those changed depending on how many were in our sample size. And so we were looking at trying to find those two different values and paying attention to whether you use the calculator doing the z interval or on the calculator using the t interval. Now, I do want you familiar with how to read information from those tables, how to use the tables as you're doing it. Don't just completely be confident in using the calculator and not understand how to do it without the calculators as you go. And then today we're going to look at estimating the population variance. Obviously, if we're talking about the population variance, we don't know the population standard deviation. Because what is that relationship between the variance and the standard deviation? Standard deviation is the square root of the population variance. And so we have that relationship as we're doing this. So this will be our last unbiased estimator that we get to do. In this section, we introduce the chi-square probability distribution so that we can construct confidence interval estimates of a population standard deviation or variance. We also present a method for determining the sample size required to estimate a population standard deviation or variance. Important note, this section does not have a calculator shortcut to use. So you have to use the table and the formula on this section. Absolutely. Yeah. No, I'm not going to turn it into, let's memorize these formulas.
Well, I didn't know if we were going to have to bring our own.
No, I'll give you guys mine because I don't want you to, I want to make sure it hasn't been written on. All right, so our chi-squared distribution. This is our symbol for chi-squared. That is not exactly an x. That is the chi, the Greek letter chi. And so this is your chi-squared is the sample size minus 1 times the sample standard deviation squared divided by the population standard deviation squared. And so now you know we've already looked at our tables being a z-score tables. We've looked at the t-score tables. Now we're going to have our chi-squared tables. And so we'll have a new table that's looking at this different distribution. Notice this one also depends upon your sample size. And so our sample size is going to be a part of what we have to look at as we try to determine what that chi-squared value will be. Again, our degree of freedom is the number in the sample minus the 1. And so that's already kind of built into this equation as we're doing things. And so that is still your degrees of freedom as we look at it. So notice it's just looking at that ratio between the sample standard deviation and the population standard deviation, what your chi-square distribution is. Properties of this distribution. The chi-square distribution is not symmetric. So our normal distribution had a nice symmetry, had the good bell-shaped curve. The t-distribution had the nice bell-shaped curve. This one doesn't. So this one is not symmetric. As the number of degree of freedom increases, the distribution does become more symmetric. So notice that this one is going to have your tail going off to the right farther, so it's skewed to the right. So a lot of more of your values are over here to the left, and it just keeps going to the right a lot farther. As you approach, so this one's got the degree of freedom of 10 compared to the degrees of freedom of 20, that this is getting to be a little bit more like a normal distribution. So it's getting to be more symmetrical, but it's still not there. That tail goes off to the right a little bit farther still, even with this 20 degrees of freedom. Also, the values of a chi-squared can be 0 or positive, but they can't be negative. That makes sense if you look at where it's coming from. I'm going to square my standard deviation, positive number, square my population standard deviation, positive number. The sample size minus 1, you're never going to have a sample size smaller than 0. You're not going to have a sample population smaller than more than 2 at least. And so you're really looking at having to have positive numbers in here. And so when you're looking at doing this, you're always going to get a positive value. The smallest you could possibly get is 0 if you had no variance when you're looking at something as you're doing this. And so you're always going to have positive values or zeros. The lowest you can get, you won't have a negative chi-squared value. So when we've been doing things, your negative z-scores just meant it was below the mean. Your negative t-scores meant it was below the mean. You're not going to have a negative chi-squared value. The chi-squared distribution is different for each number of degrees of freedom. And our degree of freedom is our sample size minus 1. Again, that determines how many values you would need to have to be able to go back and refigure out what you originally had. As the number of degrees of freedom increases, the chi-squared distribution does approach a normal distribution, but it's still not going to have any negative values for those. So it may look like a normal curve, but it's not going to have your mean of 0 and your standard deviation of 1. It just may have a normal distribution. So some more properties. In table A4, each critical value of chi-squared corresponds to an area given in the top row of the table, and that area represents the cumulative area located to the right of the critical value. Everything else we've done, your area was to the left, except for this one, and this one goes backwards, and it's the area to the right. And that's listed at the top of the table, so it's not like we're trying to surprise you with it. So if we look at table A4, I don't have it on there. So as we're looking at table A4, notice it does tell me this is the area to the right of the critical value, so paying attention to that detail being on here. We have the degrees of freedom listed along the horizontal, or along the left side. Along the right, or along the top, tells me the area to the right of my critical value. And so depending upon the degrees of freedom and what we would have as our critical values, or our alpha, then it's going to determine what we're going to have. Our confidence level that we want to have will determine which ones of these we're going to use. So if we look at some examples, oops, you guys can't see what I'm looking at. Looking at another example, critical values of the chi-squared distribution. If I wanted to have, so it's telling me I have a degrees of freedom of 9. If I want to figure out what would be the chi-squared, what would be those critical values to give me 0.025 in each of my two tails. And again, notice how it does not have the normal distribution, that it is skewed to the right. So I'm wanting to have the 0.025 in the left tail, the 0.025 in the right tail. If I want to figure out the 0.025 on the right tail first, well, if we're doing the right tail of having 0.025 on the right tail, the area to the right is the 0.025. My degree of freedom was 9, which meant there were 10 in my sample to give me a degree of freedom of 9. And so what do we end up getting? Okay, the 19.023. Now, what would I have for my left tail? And so the way we write that, because you do have two critical values, it is chi-squared on the right. We use a little sub r to say that that is the right chi-squared value. To get my chi-squared on the left, what would be if I want to have 0.025 on the right, or I'm sorry, 0.025 on the left, what's the area on the right? .975 would be the area to the right. So with your degree of freedom of 9, 0.975 as the area to the right, should be coming up with a 2.700. Everybody reading those okay? Because like I said before, this one does not have a calculator shortcut, so you have to be able to read these tables. Questions getting that? And I think if I remember right, I think I'll be having some questions on there of having you guys be able to read the other tables also. But this one, you have to be able to use the tables and do the formula to get your answers. All right, looking ahead first before we start introducing the formula. Sigma is your population standard deviation. S is your sample standard deviation. N is the number of sample values. Chi-squared, with that little sub-L, is your left-tailed critical value of chi-squared. Chi-squared sub-R is your right-tailed critical value of chi-squared. Now, if sigma is my population standard deviation, sigma squared is my population variance. S is your sample standard deviation. S squared is your sample variance. Because remember, your standard deviation is the square root of the variance. Your variance is the square of your standard deviation. Those two things are related. E is my margin of error. How far off am I? To be able to use this, to be able to try to find a confidence interval for your sample standard or for your population standard deviation or variance, first of all, the sample has to be a simple random sample again. The population has to be normally distributed values. There is no magic. If it's big enough, it's good enough. Because we're trying to figure out what the variance is, what the standard deviation is, so we cannot have a large enough sample to kind of get those things to work themselves out. And so you have to make sure that you have something that's coming from a normal distribution. I cannot estimate the variance for something that is not with what we've been doing so far. So we cannot have a sample size is not important enough on that one to say it's big enough that we can average those out. Questions on being able to use this? All right, then to find my confidence interval. Rearranging that formula we had for chi-squared a little bit ago, we're getting that our chi-squared value is the standard deviation or standard sample population variance is what I'm looking for, has to be between the sample size minus 1 over the sample standard deviation over the chi-squared on the right side. And so that is looking at having your critical value from the right, which is your number, your bigger number, has to go on the left because dividing by a bigger number makes your answer smaller. Sample size minus 1 times the sample variance over the critical value from the left, so your chi-squared on the left, because that'll be your smaller value. Dividing by your smaller value gives you your bigger answer. So those are going to be the formulas we're going to use. If I'm wanting, so this gives me variance. How do I get from variance to standard deviation? Square root. So to get to my square root, or to get my standard deviation, we'll just square root each piece. And we already know our answers are positive numbers because squaring a number will make it positive. Sample size minus 1 will be positive. Chi-squared is going to be a positive. So you were dealing with positive numbers. So square rooting will always be possible. One thing to note, on your reference card, I don't give you the variance. I'm sorry, I don't give you the standard deviation. I do give you the variance. If we look at the formula, on here, our reference sheet for our confidence intervals, we have proportions, the mean with and without the standard deviation. We have variance. I don't give you standard deviation. You have to remember that to get from variance to standard deviation, you square root each piece. So you have to remember that you're going to take that original formula and square root each part to be able to find what the standard deviation is. And standard deviation is more frequently what's asked for than what the variance is, because the standard deviation uses the same units as whatever the measurements were already being measured in before. Variance's units are going to be square units, which sounds kind of strange. All right, then let's look at doing an example. If we look at number 20A, pulse rates of men and women. Data set 1 in Appendix B includes 40 pulse rates of men, and those pulse rates have a mean of 69.4 beats per minute and a standard deviation of 11.3 beats per minute. The data set also includes 40 pulse rates of women, and those pulse rates have a mean of 76.3 beats per minute and a standard deviation of 12.5 beats per minute. Part A, construct a 99% confidence interval estimate of the standard deviation of the pulse rates of men. So if we look at finding the stuff for the min, first of all, am I wanting standard deviation or am I wanting variance? Okay, so standard deviation means I'm using the square root or I'm not using the square root. Okay, so I'm using the square root. So that's just sigma that I'm trying to find. So I'm using this formula. From what I have, what do I know? Do I know n? What is n? What is, do I know s or do I know s squared? Okay, I know s. I know the sample standard deviation was what? 11.3. So now I've got to find my chi-squared. I've got to find my critical values. If I want the right one first. Okay? If I'm wanting to find my right one first, how confident do I want to be? Okay, I want to be 99% confident. If I'm 99% confident, what's the area to the right? It's not 0.01. If I'm 99% confident, I'm splitting it between two tails, so each tail has, okay, that 0.005. So we're going to take that 0.01 and cut it in half to give some in each tail. So, what's my degree of freedom? What was my degree of freedom? Which is 39. So my degree of freedom is 39. So what are my critical values? What's my chi-squared on the right? Wait, yes. Sorry, I was looking at the wrong problem. Are you guys agreeing with that one? Now let's go ahead and find chi-squared on the left also. Do you guys agree or disagree with Aaron? Okay. So we've got the 20.707. So now we have to plug those into our formula. So as I'm using my formula, I'm going to take the square root of sample size minus 1, so 40 minus 1 is 39. The standard deviation squared, so I'm taking the sample variance, so I have to do the 11.3 and square it. I would say probably one of the common mistakes I see is you guys forget to square that value. Now, the chi-squared on the right, this value is already the squared, so your chi-squared is the 66.766. I don't square that number because that is already a squared value. That is the chi-squared value. So we'll have that 66.766. Again, I'm taking that number from the right and putting it on the left side because you're dividing by the bigger number, so you'll get your smaller answer over here. And then we'll take the square root of the 39 times the 11.3 squared over the chi-squared on the left, which was the 20.707. I'm going to give you a little bit to your calculator by those two numbers. Check and see if you get both those. One thing I just noticed a couple of you guys doing, and I want to mention this one. It's really close. After you put that into your calculator, so that's the first answer, you don't have to retype the whole entire thing again. If you hit second and enter, so right above enter says entry, that takes and retypes what you just did. So if you have something small you wanted to change, like in this case, we're just dividing instead of by that, we're dividing by the 20.707. You can just hit second and enter and let it retype the whole thing for you, and you can just type over those pieces you need. Or just change those little pieces that you need instead of retype the whole thing each time. Questions there? Now, the reason I showed my work in the middle, excuse me, this was asking for my standard deviation. This is telling me I am 99% confident that the population standard deviation is between 8.6 and 15.5, what was this, beats per minute, would be what I'm looking at. So I'm confident that I've got the standard deviation captured in there. I'm 99% confident I got it captured inside there. The reason I showed this work between, if I was asking for the variance, before I square rooted it, that would have been the variance. So if I had taken the square roots off and I squared this, that would have been my variance. That my variance, I would be 99% confident that my variance of my population is between 74.6 and 240.5. Now, why do I keep rounding to one decimal? Okay, my original data that I was given, my statistics that I was given, was rounded to one decimal. And since I've already rounded that, that's rounded one more decimal than what the true data that we had was taken to, we have to keep rounding it to the same place value. So same rounding rules we've been looking at. If you have the statistics given to you, round to the same place value the statistics were. And so before, we've always been rounded to the same place value the mean was. Here we're rounding it to the same place as the sample standard deviation was. If you are given the original data, I won't do that to you in these problems, but if you were given the original data, you'd have to round it to one more place value than what the original data was. The reason I won't give you the original data is if you were given the original data, you'd have to use the one variable statistics to calculate out what the sample standard deviation was, so that you could plug it into this formula and be able to use it. So it just adds another dimension of steps of calculating out the standard deviation. Questions on this one? Let's look at number 22 then. Designing the, oh, I said I wasn't going to give it to you, and then here we are giving it to you. Designing theater seats. In the course of designing theater seats, the sitting heights in millimeters of a simple random sample of adult women is obtained, and the results are listed below. Use the sample data to construct a 95% confidence interval estimate of sigma, the standard deviation of sitting heights of all women. Does the confidence interval contain the height of 35 millimeters, which is believed to be the standard deviation of sitting heights of women? So, where do I begin? If I'm wanting to use my formula for standard deviation, what do I need to find first? Okay, I've got to find the standard deviation. So how do I go about, because I've already said there's not a calculator shortcut to do this whole thing, but how do I use the calculator to find S? Okay, put this into my list. So go to your stat and edit. Put this into your list. Now that I have it in my list, what do I do to get the standard deviation? No. We're not going to do the t-interval because I'm not wanting to find the interval of the values of what the mean was. I want to actually know what is the sample mean. Well, I don't care about the sample mean. What is the sample standard deviation? I need to know what S is. Okay, go to Stat, arrow over to Calculate, and which one are we going to calculate? The very first one, that one variable statistics. This is taking us back to Chapter 3, because when we find the one variable statistics, and if it's of list 1, you can just hit Enter. If it's somewhere else, tell it where. This is back in Chapter 1, told me what the sample mean was, the sample standard deviation. If this was a population, what the population standard deviation was. You can even go down and find your different quartiles. This is what I use every time when you guys take a test to give you the statistics on your test information. But what piece is the piece I care about here? Just S. I just want to know what is the sample standard deviation. Now, don't round too much too soon. In the end, how many decimal places am I going to keep on this problem? Why 1? Okay, 1 more than the data. Now, for the middle of the work, because we're going to use S in the middle of this whole calculation, keep extra decimal places now. So here we need to keep at least 3, maybe 4 decimal places just so we don't have any kind of rounding error in the middle of it. So right now, let's go back to the flip page we're going to do it on. Right now we're going to go ahead and keep the 4 decimal places. So I'm going to use my S as being the 34.9805. How confident do we want to be in this problem? Okay, I want my confidence level to be 95%. How many are my sample? Okay, my number of my sample is 12, which means what is my degree of freedom? So I want you guys to go and find your chi-squared on the right and your chi-squared on the left. What are you getting for chi-squared on the right? Thumbs up or thumbs down with Aaron's statement? How many of you guys think that's right? How many think that's wrong? How many of you, just do thumbs sideways if you don't have a clue. Okay. That tells me I need to look at doing this one with you guys then. If we look at our table, so look in our chi-squared table. First of all, for the degrees of freedom, what am I going to use? Okay, I'm going to use 11 degrees of freedom. If I want chi-squared on the right, let me go back over here to do this part first. If I'm doing chi-squared on the right, if it's 95% confident, what's the amount in the two tails? Okay, 5% together is in the two tails, so that means how much is in this tail and how much is in this tail? Okay, 0.025 in this tail, 0.025 in that tail. So now if I'm looking up the chi-squared on the right, so I'm doing this guy first, what is the area to the right? 0.025 for your degree of freedom of 11. So if we come back to our degree of freedom of 11, we are doing the 0.025 on the right and finding that place those two meet. It gives us the 21.92. Okay, now find your chi-squared on the left. Okay, if I'm doing the chi-squared on the left, what is the area to the right? If this is 0.025 over here in this tail, what's the area to the left? Okay, we're looking up the 0.975. Still having my degree of freedom of 11, doing the 0.975, and so you should be getting 3.816. And so those are the things we're going to plug in. And so we're going to take the square root of n minus 1, so that's going to be your 11, times the sample standard deviation squared, divided by the chi-squared on the right, which was the 21.920. We'll take the square root of all that, be less than my population standard deviation, and then doing the same thing on the right. Questions getting that the standard deviation is between 24.8 and 59.4. And again, we're just rounding the final answer to one decimal place, but you're keeping extra decimals through the middle of the problem. If I asked you for variance, you would not square root it. And that's the only difference, is you would just avoid square rooting if you want the variance. Because your variance is your sigma squared. Okay, if I want to find the sample size is a lot more complicated because your whole chi-square distribution changes depending on your sample size. And so it gets a little bit more challenging to try to figure out what it is. If you look at page 376, it kind of works through it with you of what you have to do. First question it's asking, do I use the left side or the right side? Am I looking for the sample size for a variance, or am I looking for the sample size of the standard deviation? So that alone just cuts it into, am I looking at the left half or the right half? Then when I try to decide if I'm on the top half or the bottom half, it's asking, do I want to be 95% confident or do I want to be 99% confident? And those are the only two options you'll be asked for on these. If you want to do a standard deviation and you want to be 95% confident, you're in this upper right corner. And then it's just asking, how do you want your standard deviation to be within 1%, 5%, 30%? You know, how far off? What is your plus or minus of the percent value from your standard deviation? That decides your sample size. If I only want to be off by, I want to be 95% confident that I'm only off by 1% on the standard deviation, I need 19,205 samples, values in my sample. Versus if I allow it instead to be off by 20%, plus or minus 20%, then I only need 48 in my sample. If I'm wanting to be 99% confident instead of 95% confident, even if I'm at the 20%, I went up from 48 to needing 85 of them in my sample. So it's greatly increasing it if I'm wanting to be 99% confident versus 95% confident. So just being able to read this table and just figure out which piece you're in. So let's look at number 14 on page 378. So number 14 is asking, find the minimum sample size needed to be 95% confident that the sample standard deviation S is within 30% of sigma, which is a population standard deviation. Is the sample size practical in most applications? Okay, so first of all, am I on the left half or the right half? Why the right? Okay, I want in standard deviation, not the variance. Okay, am I going to be in the top half or the bottom half? Why? Okay, I want to be 95% confident, so I'm in the top half. Which percent am I allowing my error margin to be? Okay, I'm allowing it to be 30% off. So how many do I need in my sample? I need 21. Is that practical? Yeah, that's practical. Would it be practical to be only off by 1%? Having 19,000 in a sample doesn't sound very practical to be able to do. It's a huge, huge sample size. Even 768 is a pretty big sample size. You're really looking at something that's pretty big. It's a big sample size when you're looking at doing something. Usually that's more of one of your professional Gallup polls and that type of thing that would be getting that largest sample size. Questions doing those? Okay, I thought I had a page in there. I want to do a couple of review things. I thought. If you know, just do it on this page. If we go back to proportions, if I know that in my sample I had 520 in my sample and I had a success of 110. First question I'm going to ask is, what is p hat and what is q hat? What is p hat? What was it? Either one. Okay, 11 over 52, which is approximately the 0.2115. That's an approximately. That's horrible. And let's see, I guess with these, we were rounding them to 3 decimals, weren't we? This would be approximately 0.212. What would q hat be then? Okay, that minus 1. And so we would be looking at having, if we subtracted that, would be the 41 out of 52, which is approximately 0.788. Because p hat is your probability of success, q hat is your probability of failure. Now, if I wanted the confidence interval, let's say I wanted to be, let's go easy. Let's do 95% confident that I was capturing the true population proportion. What would I do? Okay, I'm hearing Aaron wanting to use his calculator. How would you use your calculator? Okay, go over to your stat, go to your tests, and you're going down to the A, which is what it is on mine too, the 1 proportion Z interval. Because it's a proportion that you're looking at, and you're using, it's just one proportion that we're dealing with. We're only dealing with one set of data. And so we're getting to use our Z-scores when we do that. So when I do that, what do I put in for X? Okay, it's the number of successes. What do I put in for N? It's the number of my sample. Confidence level is the 0.95. And then we can calculate that out. Now we could have also used the tables. If I was using the tables, if I was using the formula, there it is. So if I was using my equation, it takes my margin of error, so you're going to take your sample proportion minus the margin of error and plus the margin of error. To find the margin of error, you're taking the z-score of alpha over 2 times the square root of p hat times q hat over n. What is z of alpha over 2 in this problem? Okay, alpha over 2 is your 0.025 because your alpha is, if you're 95% confident, alpha is 5%, cut in half is the 2.5%. What is z of 0.025? What am I looking up in my table? What am I looking up in here? 0.975. So I'm looking that up in the body of my table. So when I find the 0.975, where's my finger? So when we're trying to figure out what that is, we're coming over here. It's the 1.9 going up to the 6. So it's going to be the 1.96 to be the z-score that you'd be using. Make sure you're able to find those values. And so then you could plug that into the formula, and I'm not going to worry about taking the time to plug that into the formula. What if we were talking about, what if I wanted to find the mean, and I knew I had a sample mean where the sample mean is, I'm going to make up some numbers, 2.5, my population size was 40, so we know for sure that we've got the more than 30 in our sample, and I want to be, let's go with 99% confident. And I need a standard deviation. Let's do our standard deviation of being 0.41. I guess I should round to the same decimal. Let's do 0.4. From what I just gave you, what do I use? If I want to find my confidence interval. I'll even let you talk about using it on the calculator. What would we do? Okay, stat, test. Trevor wants to use the t-interval. Do you guys agree or disagree? Why is it the t and not the z? I don't have the standard deviation of the population. I have the sample standard deviation. I don't have the population standard deviation. Now, on the test, don't count on me being nice to you and giving you that it's s equals 0.4. I will just tell you things like, from my sample, I had a sample standard deviation, or a sample, from the sample we got the statistics of a mean of 2.5 and a standard deviation of 0.4. You've got to recognize that came from the sample, it didn't come from the population. On the other hand, if I say, and the population had a the population had a sample standard deviation of 0.4, then you have to recognize which one of those two you have. If it's the population, we get to use the z. If it's the sample, we get to use the t-interval. Now, if instead I made you figure out what the t-score and made you do something to use the formula, because if we're using the formula, wrong side. If I'm using the formula when I don't know the population standard deviation, we have to use the student t-scores. What would be my student t-score on this problem? The degree of freedom is what? 39. Do I know the area in one tail or two tails is what? Okay, 1% and two tails, so that's that first column. If we use the first column down at 39, the t of alpha over 2 is 2.708. So make sure you guys read the questions carefully, because I will completely get a different answer. And let me go and just do this one real quick. If we did the t-test on this one, came from our stats, the mean was 2.5, standard deviation was 0.4, sample size was 40, confidence level of 95%. So it's giving me between 2.4 and 2.6. If all I did was change, instead of having the sample standard deviation, if that was that the population standard deviation was 0.4, we just completely changed what we do, because now what do we use instead? Stat, test, which one? Okay, now we'd use a z. By the way, you can just hit 7 to get z. You don't have to arrow all the way down. You can just hit the number 7 and get there. Same thing with the t, you could just hit the number 8. So we still have the test. We're going to have the standard deviation of the population. So notice it does tell you, hey, you're looking for sigma here versus looking for S before. 2.5, 49. And so now it's giving me, oh, this time it actually gave me the same answer. Usually it doesn't. Usually you do get a different answer depending on if it's a sample or population. On this one? So it's not 2.4 to 2.6? Did I type something in wrong? 0.4. Oh, I forgot to change that to 0.95, or 0.99. I think I did that on the other side too. No, I did it on that one. Okay. All right. I will have your guys' test in the ARC tomorrow morning. So you can either take it tomorrow or Friday. Do your homework first. If you have questions, let me know. I do have your projects also. We'll have the projects due on Monday. It's just wait and turn your homework in on Monday. Be fine. I think there's 4 there. Thank you. So have a good weekend. See you guys next Monday. Don't forget to take your test.